Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. And in today's episode, we sat down and talked to Dr. Rana, who is a specialist in cryogenics. Hannah graduated from University of Oxford, where she did her PhD and worked as a postdoc. She has also worked at CERN and ESA and currently is cryogenic detectors researcher at NASA Jet Propulsion Laboratory, as well as cryogenics lead at Neutron Star Systems. She has also had the amazing luck or opportunity, however you want to call it, to be part of the 2022 international cohort of Schmidt Science Fellows and is on the 30 under 30 European list of Forbes in the category of science and healthcare. She's also the first researcher on our show that does not work in Luxembourg but has a strong link with the country. You'll find out what kind of a link. Our guest today is Dr. Rana from NASA and many other places. And normally I already move straight to the research, but you might be wondering, why is she here on the podcast? So there is a link to Luxembourg. But first of all, thank you very much, Hannah, for accepting our invitation.
Thank you so much for having me, Hannah.
Okay, so as far as I understood, and correct me if I'm wrong, the link for you is not being born in Luxembourg, but you lived because you don't anymore in Luxembourg for many years.
Yes, that's correct. So I was born in London, but I moved to Luxembourg when I was a child. And I grew up here. I went to school here. My fixed family home is still here. My parents are here. And I'm regularly here. So I even try to work remotely as much as I can from Luxembourg. So I do spend maybe more than 50% of my time in Luxembourg.
Okay, so the link is very strong. Hopefully one day it will be 100%, but we will talk about it later. I always try to, the researchers that kind of slip out and leave Luxembourg, I always try to convince them to come back. So yeah, but I'll do that later. First of all, as I could read on different sites that I visited, you have a collection of fellowships and you have worked in many different places. So it was CERN, ESA, and now it's NASA, right? The NASA thing is very, very recent. You are basically starting, aren't you?
Yes, so I've actually started remotely. I had a bit of an issue with my passport being stolen. And then, I'll be heading out there in a couple of days, actually, yeah.
Okay, so at NASA, what do you specialize in? What are you going to do there? Or what are you doing now? Because you've already started.
Sure. So I'm working within the same field that I was working in at Oxford, where I was doing my PhD, and then I did a short postdoc as well. And there was also some collaborative work with NASA during this postdoc time as well. So that's the kind of link there. And I'll be working in cryogenic space instrumentation. So working on cryogenic instruments for space detectors and instruments on board spacecraft.
So first definition is coming right now. What is cryogenics?
Cryogenics, broadly speaking, is a field where we work to bring things down to low temperatures. So cryogenic temperature is defined as anything that is 100 Kelvin or below. Some definitions on this can vary, but that's the general definition for cryogenic temperature. And 100 Kelvin is about minus 173 degrees Celsius. So anything at that temperature or lower will be cryogenic temperature. And then in terms of space cryogenics, what we're trying to do is achieve cryogenic cooling for instruments on board spacecraft.
I know that also in that topic you prepared the pub quiz question. So before we get into detail and we talk a little bit more about your research, can you ask the question?
Sure. So today's pub quiz question is, if space is already so cold, why are we cooling in it?
Okay, great question as usual. And for those of you who are listening for the first time, the answer to this question will be at the end of the podcast and maybe also during, because it's very much related to what you're doing, Hannah. So we might be discussing it too. But anyway, I also have never thought about it, how important it is. And now that I read a little bit more about cryogenics, I got to know more, you're doing that for, as I said, for space. But also I know that cryogenics can be applied in other disciplines. What are these?
So cryogenics is useful in a range of applications on Earth as well. So it can be used in the food storage industry. It has many, many uses in the superconducting industry. So, for example, CERN, where they have the Large Hadron Collider, in order to achieve that acceleration in particles, you use accelerating cavities, which are cryocooled, in order to reduce something called electron field emission, which allows for the particles to be accelerated to higher energies. And also there's use for cryogenics in the medical world. So it can be used in MRIs, or it is used in MRIs rather. So MRI machines will have cryocoolers that help to improve the intensity of the magnetic field for the magnets being used. And also in cryogenic surgery. So for example, if you want to treat somebody with an arrhythmia in their heart, you can actually do something called cryosurgery, where you cryogenically zap some of their cells in their heart, which are actually causing the electrical distortion, which then kills them with those cells, and then removes the arrhythmia. So it's a great way of doing a non-invasive medical procedure on someone's heart. And that's just one example. There are now other applications in the world of surgery for cryogenics as well.
When it comes to cryogenics, is that a new field or it's been with us for quite some time?
So cryogenics has been being developed for, I'd say, the last maybe 40 years or so. One other application I just recalled is that for magnetic levitation trains. So, for example, if anyone's ever been to Japan and been on the Shinkansen, the bullet train as they call it there, those also have dedicated cryocoolers on board. And I think those were one of the first areas of development for cryocoolers and cryogenics in this kind of a big scale application. So definitely around 40 years or so, 50 years even. And in terms of space cryogenics, the first space cryocooler, it's called the Oxford Cryocooler. It was actually built in my lab at Oxford, and that was back in the 80s as well. So that kind of kicked off the field. So since then, really.
Okay, so you mentioned a cryocooler. So you need a cryocooler to cool whatever you're applying it to. Very simple terms. I know that this is going to be really tricky for you to explain, but how does it work? How do you get these temperatures, this low temperature with a cryocooler? Is it possible to explain it in simple terms at all?
Sure, yeah, I can definitely give it a go. So basically, the cryocooler, it uses typically helium gas, and it's designed in a way where you are compressing and expanding the helium gas, and you're running something called a thermodynamic cycle. And as you run that thermodynamic cycle and you expand and compress the helium gas, you're able to create a very sophisticated series of pathways for heat flow, so that you are able to reject heat in certain regions of the cryocooler, and you're able to pull heat from a source in another end of a cryocooler. So if you think about it this way, it's kind of like a heat exchanger, where you're extracting heat from one region and then you're dumping it somewhere else, basically. If I'm to give a very reduced kind of explanation of it. And then ultimately, that means you have a warm end and a cold end. So the cryocooler's warm end is where the heat is being channeled to via this helium gas. And then the cold end is where the gas is at its coldest. And because it's at its coldest, it means that at that region of the cryocooler, if you integrate your detector, you integrate your focal plane assembly, which will be the part of the telescope that's doing the detecting effectively, then that very, very cold helium gas can then snatch heat from that detector that is integrated and cool that detector. And then that channels the heat back down to the warm end.
Okay. Yes, I'm still analyzing that. I'm probably going to listen to it once again to get really the grasp of it all. But as usual, when we talk about space applications and we're using a gas, in this case helium, how will that work, especially when we go into deep space or whatever, we need a cryocooler? Can we source helium in space?
That's a really good question. So actually, what you would do with a cryocooler is you would fill it up with helium on Earth, and then you seal the cryocooler. And so that hopefully will never be opened. You then place that in its entire insulated state into the spacecraft, integrated into the Space Telescope as it is. And the helium doesn't actually need to be replenished. So the amount you've put in is what you would just keep expanding and compressing and expanding and compressing, and while you're running this continuous thermodynamic cycle. And so unless you have a leak, which can happen and is one of the most dreaded things in the world of cryocoolers, unless you have a leak, then you don't actually need to refill it.
We're talking about cryocoolers. I did not mention it before, but that was also the subject of your PhD study, right? And a lot of the things that the articles that you've written and all that. So now I understand more or less how it works as such. But what about the size? How big does it have to be?
So cryocoolers can vary greatly in terms of size, depending on how much you're trying to cool. The one that I worked on wasn't more than maybe 50 centimeters by 50 centimeters by 50 centimeters, so 50 centimeters cubed. But they can be much, much bigger than that. So, for example, the ones that might be used for an MRI machine, or the ones that might be used in quantum computing experiments, those can be the size of a room. So, a very large room, the cryocooler can fill that. And it's effectively the compressor that is filling that size in order to generate a very cold temperature and also to have a very high cooling power. So the cooling power is effectively how many watts of heat can you extract from the object you're trying to cool, right? So if I've got, for example, the cryocooler that I built for my PhD, it was able to extract about 4 watts of cooling power, meaning that if 4 watts of heat is generated by something integrated at the cold end of my cryocooler, then my cryocooler will be effective in removing that heat. So for other applications that have very, very high heat loads you're trying to cool, you need an incredibly high cooling power. And so you need an incredibly large compressor to do that. So the volume of cryocooler can really, really vary depending on the application.
And then unfortunately, you also increase the load of the spacecraft, right? Don't you?
Exactly. So that's one of the key challenges in the design is that the second you increase the mass of the cryocooler or anything that you're designing for a spacecraft, you've then increased the mass of the overall space mission, and then you require more power for that larger mass. And then usually for larger masses that require more power, you need more mass to generate that power. So it's a bit of a catch, and you have to be very careful that you don't increase your mass too much. So it's one of the main things you try to optimize.
And then I don't think we mentioned that, so I just kind of moved away from the space application. But why do you need a cryocooler in space?
Why do you need a cryocooler in space? I guess this is coming back to the pub quiz question, I guess. So really, the reason you need to cool in space is because one thing to set the context is the fact that although space is very, very cold, the spacecraft that we design, build, and test on Earth are then insulated, right? So we seal them; they're completely insulated. As I mentioned with the cryocooler, it's the same for every system on board, and so that means that internally, the temperature of the spacecraft is room temperature on Earth. So it's the same temperature as the room in which it was built and assembled. And so then that gets sent into space, and that temperature is effectively maintained. Well, it will also increase, actually, because you put a bunch of electronic components on board, and those will generate a lot of heat. So it's as if you were to imagine having a small cupboard and putting, 20 computers in there, switching them all on, closing the cupboard, locking the door, sealing it, and then hoping for 10 years that those computers run, not generating any heat and not causing a fire. So it's a similar sort of problem with a spacecraft, really. You've got all these components on board that are going to be generating heat, and that heat needs to then be rejected continuously throughout the spacecraft lifetime. Now, that cooling can be done relatively passively. You can have some active elements to it, but relatively passively, because space is so cold, you can design heat pathways that can reject that heat via a radiator. So a radiator simply meaning a surface on the spacecraft exterior that can radiate out that heat to 3 Kelvin cold space. But the reason we use cryocoolers, which is a form of active cooling, so you're actually putting energy in to get that cooling, whereas with passive, you're just emitting the heat into space. With active, you need that for things like space telescopes and space detectors. So space detectors, they are subject to a phenomenon called thermal noise. And thermal noise occurs in electronics and conducting devices when there is some form of thermal agitation. And so that thermal agitation can interfere with the signals that you're trying to detect, right? And if the signal you're trying to detect is particularly weak, which they can be in space, then obviously that diminishes the quality of the signal you're detecting, and it means you also have interference. So you're not able to differentiate with the signal you're trying to detect. So we need to eliminate this thermal noise, and that's what we do cryogenically. We cool down the detector to a cryogenic temperature so that we can eliminate this thermal noise. And thermal noise is something that increases with temperature. And then that makes the detector in a telescope more sensitive to much weaker signals. And that's a very, very key aspect of astrophysics research, because the weaker the signals we can detect, the more sophisticated the discoveries we can make in space. So we can detect things that are much further away. We can detect things that are more subtle. So that really, the cryogenic instrumentation is really one of the driving forces behind being able to make more sophisticated discoveries in space.
So that basically means that any detector you are using actually will need a cryocooler.
Yes. Yes, it will. I mean, it depends on the detector. Some detectors might not need a cryocooler, but most detectors do.
That's brilliant field of research, because you'll always be needed when it comes to going to space, because there will be always need for better and more reliable cryocoolers. Is that the reason you chose this field?
I guess partly. I had appreciated that. So I joined the European Space Agency on the graduate program in the field of thermal control. And so cryogenics is a subfield of thermal. And it just so happened that actually my supervisor at ESA, he was the cryogenics expert. And that's how I was introduced to the field. And once I started working on cryocooling instruments, and I saw how they were quite fundamental to a lot of discoveries, and it meant that I could then work on lots of different astrophysics related missions. I think that kind of enticed me to move into this field and focus in on this kind of research.
And I think at this point we need to mention what you've done so far, because there are quite a few very interesting bits and pieces, let's say, and organizations and institutions you've been to. So what you mentioned already is that you worked at the University of Oxford, right? And already there you were focusing on cryogenics as such. That was your research. You've been at CERN, ESA, and now NASA. So I understand more or less University of Oxford. What about CERN? This was also cryogenics, right?
So I was working on accelerating cavities, which are then cryogenically cooled, but I wasn't actually coming in on the cryogenic aspect at this time. I was working more in applied physics. So I was working in, well, cryogenics is also applied physics, but I was working on a slightly different aspect. So I was working on the surface finishing of the accelerating cavities. So the Large Hadron Collider is a 27-kilometer long particle ring that enables particle collisions. And along this ring, you have 16 dedicated accelerating cavities. That's what we call them. And they are effectively these elliptical structures there are 16 of them lined up in a sequence. Or they were at the time that I was working on them. I know that since then they've tried to modify the design a bit, so I haven't kept up to date with the number exactly.
They're actually relaunching it right now. I mean, it's been running, but I think from tomorrow, if I'm not mistaken, it's going to be just really running 24 hours a day.
Exactly. Yeah, they're starting it up again, and there will be a live watch of the run up. So these cavities, their internal surface finishing has to be improved to remove electron field emission, which is a phenomenon that can occur with superconducting material surfaces. whereby they will degrade the radio frequency energy that is being given to the particle as it passes through the accelerating cavity. So that's the aspect I came in on.
Okay, and that was first, right? And then it was ESA.
That's correct.
And at ESA, that was exactly what, if you could tell us?
Sure. So at ESA, I was working in thermal. So I was a spacecraft thermal engineer. I was working on the temperature management of spacecraft as a whole, but also instruments on board spacecraft. And then within this time, I also then started to work more on cryogenic projects as well. But I did do general thermal engineering, and my main project while I was at ESA was the lunar lander, the Luna 27 mission to the South Pole of the Moon.
What was that mission about?
So that mission was basically going to the Aitken Basin, which is on the South Pole of the Moon. And it's one of the most permanently shadowed areas on the Moon. And so it's a region where we have very, very strong belief, almost scientific certainty, that there is ice below the surface there. And so the aim of this mission was to travel to the Moon, land in the Aitken Basin, and then drill for ice. So the idea was to drill below the surface, extract samples, and then actually have an in situ chemical analysis software and toolkit, really, that would be able to determine the composition of the sample and then determine if that was ice that was present. And this was a really interesting mission because not only from the aspect of planetary science do we want to determine what there is on the Moon, but also from a more kind of futuristic, spacey kind of perspective. There's a lot of talk about developing a moon village, so having a new base on the Moon where we can have, some sort of moon headquarters or something, a checkpoint in space, really. And if we were able to find a sustainable way to extract this ice and create a water supply, that would be incredibly useful.
And that's why this mission, one of the reasons, right? But you mentioned that this was this part of the Moon that is in the shadow, right?
Mm-hmm.
So then
Yes.
the thermal noise should be less, or am I not getting something?
No, that's a very good question. So for this mission, actually, I wasn't really working on cryogenics. I was doing general thermal. So not really trying to cryocool. In fact, doing the opposite. I was trying to heat the spacecraft up because it would get very, very cold. I was working at the sort of pre-concept phase A, phase B, 1B, 2 stage of the spacecraft life cycle, which meant that I was involved in defining the orbit. So after the spacecraft has been launched, what orbit will it take? What orientation will it be with regards to the sun? Because as a thermal engineer, your key considerations are where in space are you and what is facing the sun? Because remember, we don't have, how we have on Earth, we have an atmosphere, which is a sort of filter of the solar rays. In space, you don't have that luxury. So if you're facing the sun and solar rays are impingent on a particular surface, that surface will get very, very hot. Conversely, if you're not facing the sun and you're facing deep space, which is 3 Kelvin, that surface is very, very cold. So you have very, very extreme temperatures in space. So I was involved in defining the orbit that we'd be taking to get to the Moon, but then also the orbits that the lander would have to evolve into while it's approaching the Moon, and also what orientation the spacecraft should have with respect to the sun whilst doing these orbits. So there's a lot of astrodynamics and a lot of celestial mechanics involved there. And then I was also working on selecting the landing site. So where would be the most appropriate landing site, thermally speaking? And the key candidate landing site for that also, because the Moon is very hilly. There are a lot of hills, and because we're in a crater as well, there are a lot of elevated surfaces within the horizon. So one of the key considerations I had to do in that regard was understand how much heat would be emitted to the lander at nighttime. So whilst the sun's not even there, how much did those structures absorb? How much heat did they absorb from the sun during the time that we did have a bit of sun, and then how much of that would be emitted to the lander as well. So having a full understanding of all the different kinds of heat pathways that the lander could be subjected to at any stage in the mission, from launch, reaching space onwards, to landing on the moon and being present on the moon.
And it's interesting you mentioned that. I guess there must be a lot of discussions, because obviously the place which is the best from the thermal standpoint doesn't have to be the best for, I don't know, prospecting, space resources, or whatever else that the mission is aiming to achieve, right? So I guess there is a lot of push and pull on the scientist side, whoever is trying to achieve the best conditions for their field.
Exactly. That's a very good point. I think this is the fun of being in thermal and being in cryogenics, is that you aren't necessarily the first decision maker on what's being done. The scientists are the first decision makers on what's being done, because they're deciding on what the mission is going to do. And then, being in the applied physics field or in the engineering field, you just have to make it happen. So that's the fun part of the challenge. And I think because thermal is so fundamental to the operation of anything you send out into space, it means that, while I'm working in thermal, you see a range of different challenges and a range of different problems, like the kinds of issues you'll deal with when doing an Earth observation mission are so different to JUICE, for example, sending the mission to Jupiter, or the James Webb Space Telescope. So the range of different challenges you have from a thermal perspective, with the different orbits and the different positioning in space, will be so varied.
Of course. And I think another problematic could be just the temperature, the heat created while taking off and landing, wouldn't it?
Yeah.
So you have to also provide for these situations, so that whichever detectors and sensors you have and other apparatus that you have on the spacecraft does not get influenced by these very sudden increases in heat.
Exactly. Absolutely. And so we have some very sophisticated thermal protection systems that you would employ to insulate the spacecraft entirely. So the spacecraft payload is usually placed at the top of the rocket launcher, and then you're obviously furthest away from any of the exhaust. So there is insulation covering that entirety, which would thermally protect the payload as it goes through launch and as it goes through atmosphere.
With that, we finish with your work at ESA and we move on to NASA. So what is your plan for now? What are you going to take care of? Or maybe it's all you can't share with us. I don't know.
No, I can. I am still defining a lot of what I'm doing, because I'm still in the research aspect. I'm working on sort of next generation detectors, really very sophisticated kind of detectors, and developing the cryogenic instrumentation that can be used for them, and trying to cool to very, very low temperatures. So the typical kinds of temperatures you're cooling with for example, an Earth observation mission will be between roughly 50 to 80 Kelvin, to give you an example. And then for astrophysics, they'll be lower than that. So that's where the cryogenics gets very interesting. And now the kind of detector I'm working on, so the coldest temperature we've achieved in space now is with the James Webb Space Telescope. We've reached a telescope that now has an instrument on board which needs to be cooled to less than 7 Kelvin. That's the mid-infrared instrument, MIRI. So that's incredibly cold now already, 7 Kelvin. And then the kinds of detectors I'm working on are sub-Kelvin, so less than 1 Kelvin. So this will really be a very pioneering breakthrough technology. And the way in which we would do this cryocooling is something I'm still trying to work out. So that's something I'm applying my mind to for the next phase.
So that's something that doesn't let you sleep at night.
I guess you could say that. Yeah.
One of the things I was also thinking of that was interesting in the discussion, and also made me actually contact you in the first place, was that you were nominated as 30 under 30 by Forbes for Europe in the field of medicine and science, wasn't it?
Yes, science and healthcare category.
Science and healthcare, there you go. I got it wrong. But yeah, anyway, more or less the idea is there. And was it because of exactly what you mentioned, that what you're going to do at NASA, or was it for some previous work? Do you know exactly how the nominations go?
So I'm actually not too clued up on the selection process. I just know that I was nominated, and that I think there's an expert sort of panel of jury that then make the final decision. But it was for the work that I've been doing at Oxford and now at NASA as well, which is in this field of pioneering new cryogenic technologies for space discovery.
I don't know if you're aware, you were on the same list with the Italian band Maneskin and Kylian Mbappé, footballer from France. So it was interesting. I just, out of curiosity, I checked who else was there. And unfortunately, I didn't know any of the scientists, and this is so sad. I mean, I really want the scientists to be the movie star type of personas, and unfortunately, we rather know the football players and musicians, which is good as well. Don't get me wrong, but yeah, would be great to know more about the European research as such. But yes, we'll get there one day, I'm sure. And also another thing that Luxembourg was reporting on that I wanted to mention. So not only Forbes and not only other fellowships that you got and all the things, that's just amazing. Congratulations on that. Earlier on, you had this amazing opportunity to actually talk to the Nobel Prize winners. Can you tell us a bit more about that? How it happened? Was there any support from Luxembourg for that? And what was the experience? Do you still remember that? I guess so, right? I think this is lifetime experience.
Yeah, that was a phenomenal experience. I do have this slight problem these days where anything that happened before the pandemic, I'm struggling to remember. But no, that was definitely something that was deeply cemented in my mind forever. So yeah, that was a wonderful experience. It's called the Lindau Nobel Laureate meetings, and basically, young scientists from around the world can apply to be selected to attend this meeting that takes place. So it happens every year at Lindau. Lindau is the little island in the south of Germany, in a really beautiful region. And as someone who grew up in Luxembourg and I grew up going to Germany all the time, and it would be Frankfurt or Cologne or Trier, wherever. Honestly, when I went to Lindau, I couldn't believe I was in Germany. It was so beautiful there. So that's probably my ignorance there. So they have these Nobel laureate meetings every year, and then they alternate between the different subjects. So in 2019, it was the physics Nobel laureate meetings. And so if you are in the field of physics and you're a young researcher, you can apply to attend, basically. And then if you're selected, you get to go there and meet the Nobel laureates and have one-on-one discussions with them and present your own research and so on and so forth, and then meet the other young scientists as well from around the world. So it was a phenomenal experience, and I really, really enjoyed speaking to the laureates because, at the end of the day, they were just people, and they were very, very humble. They're very nice. They're very kind, and they were genuinely interested in what I was doing. They genuinely wanted to understand what I'm doing. We were able to exchange ideas. We were bouncing loads of ideas off each other, and that's a phenomenal experience to have intellectually.
Definitely. It also kind of gives you that power to pursue your interests, because, we have this tendency to think that, the youngsters, they have their ideas, but then the more experienced people don't necessarily want to listen to. But it's not true. There are a lot of scientists who are open to listen to our ideas, just like in the interview I had with Antonino Salmieri in one of the podcast episodes, where he was talking about his space law research and the fact that he was really able to present a lot of the ideas to very acclaimed groups of people and get amazing exchanges out of it. So this is always very good to have that bridge between two, three, four, five generations, how many there are. But I wanted to understand, for this particular project, was there any support from FNR as well for you to go there? Because I know that there was some link, right, with the Fonds National de la Recherche.
Yeah. So basically, once I was selected, they were actually able to sponsor me to attend, which was great. So I was sponsored by the FNR, that's what brought about the interview, really, that is up on their website. So yeah, that was the link.
So you have already the experience of being sponsored by FNR. So I can only say that once you are not so happy about working at NASA, then you come back to Luxembourg, you get amazing research grant from FNR, and you do your studies here. I mean, as you know, Luxembourg is really growing to be very strong in the space research and space, especially space resources. So I'm sure there will be a special place for you once you decide to come back.
Thank you. I hope so. Yeah, we'll see what happens.
Yeah, I understand that maybe we're not such great competition as the current employer, but who knows, you know. Would
No,
be lovely to have you back.
I'm always very excited to see what Luxembourg is doing in scientific research and across the board, really. In space, they're doing so much, as you mentioned, and also in a lot of healthcare technology and, you know, health tech and biomedical engineering. They're doing phenomenal things. So really, really impressive stuff happening, and in also in IT and in machine learning and computational systems.
Yeah,
Well.
absolutely.
So really impressive stuff.
Absolutely, yeah. And if for those of you who haven't had a chance to see us, as usual, I just invite you to have a small listen to the other episodes of my podcast, because all these applications you've mentioned, neurodegenerative diseases and in general medicine applications, and as well as IT, we've discussed. So you will be able to listen to it, and there'll be more to come for sure. But we unfortunately have to slowly finish and wrap up our podcast. And you have revealed a little bit. The question was my fault this time. I asked it at a certain moment, but I just wanted to get the link of cryogenics and your work in the space field. But I'm sure that the listeners were so in awe with all the other discussions we had that they forgot exactly what the answer was. So we can reveal it once again. So first of all, can you please remind us the question and then tell us the answer?
Sure. So the question was, if space is already so cold, why are we cooling in it? The answer is, effectively, we're trying to eliminate thermal noise for detectors in space, so in space telescopes, so that they can be more sensitive to weaker signals and detect more effectively in space.
Clear answer, short question. I think everybody will remember it from now on. And what remains is to thank you very much for today. Thank you for sharing all your knowledge. Good luck with all the endeavors, and good luck at NASA. And please come back one day. We'll be waiting for you.
Thank you so much, Hannah, for having me. Really, really appreciate it. It's been a wonderful discussion. Thank you.
And this is it for today. I hope you enjoyed the episode. As usual, don't forget to subscribe, to follow us, to contact us if you have any suggestions or comments, and of course tell others about us. I hope you enjoyed this episode. This was Silux, and my name is Hanna Siemaszko.